Ladies and gentlemen, my name is Seyed. I hope you are all excited to delve into the fascinating world of optimization in lithium-ion batteries structures today. In this presentation, I will explore how optimization techniques can be applied to enhance the efficiency and performance of the lithium-ion batteries, especially in Tesla cars when it is subjected to the three-point bending test and crashworthiness test. Agenda. At the beginning, I will talk about the three-point bending test and we will compare our results with the experimental test. In the second stage, I will also explain how we do the optimization techniques and we will discuss the future works at the end. Lithium-ion batteries are rechargeable devices widely used in electric vehicles. One of the most common formats is the 18650 battery, named after, uh, let me take the pen, yeah, okay, named after its dimensions, 18 millimeter in diameter on the cap and 65 millimeter in length or height. So in the first stage, CTS scan is we use CTS scan to identify the geometry of the lithium-ion batteries. CTS scan is a technique used to analyze and evaluate the internal condition of lithium-ion batteries without disassembly. In most of the works done in the literature, they have to cut the sample to find out about the dimension of the inside of the battery or the shell thickness. Tensile strength measurement process. We, we cut some samples from the enclosures. You see here the blue uh, PVC part of the battery, and we just cut some samples. And one of the important thing is the samples should be properly shaped and sized according to the testing standards. We have conducted several experiments and we found that if it is not like dogma structures, uh, dogma shape actually, we can get different results here. The shell thickness of the lithium-ion batteries can vary due to manufacturing process and factors, and sometimes it can be done intentionally. The variation in shell thickness can be observed and analyzed using CT scan machine and SEM, scanning electron microscope. But for SEM machine, you need to cut the sample at each section, and actually thicker shells may provide enhanced protection, while thinner shells may improve energy density but could be more susceptible to damage. So you will see here we got the results uh, for the 18650 and the shell thickness at some sections can be seen here, and the corresponding image from the CT scan from that section is also embedded here. The first test we use is a three-point bending test. Three-point bending test is a widely used standard test out of the main four standard tests for the lithium-ion batteries in the evaluation of the battery structures. The three-point bending test involves applying a load to a battery specimen using 3 points of contact, 1, 2, 3. The specimen is supported at 2 points here, while the load is applied at the midpoint, introducing bending stress. And battery specimens were prepared according to the specific dimensions, uh, as can be seen here. We uh, did the mesh generation and abacus, and we imported our mesh to the LS Dyna software here. And samples uh, might include electrodes, separators, or full battery cells, depending on the evaluation of the objectives. I mean, in this kind of a standard, in some cases, they just consider the shell, or they just consider the jelly rolls, which is inside of the shell. But in our experiment, we consider the whole battery. So the load is gradually increased until the specimen reaches its maximum bending capacity or failure points. And during the test, the applied load and resulting displacement or deformation are recorded. So the comparison of simulation results between the MIT lab and our simulation here on the right reveals the accuracy and reliability of our approach in the simulation. Actually, in our approach, we use different element for shell casing contact model, and we also use a different kind of contact model between the nodes of the shell element and the jelly roll, which is jelly roll. I will just explain again, is just related to the components inside of the shell of the battery. So these are the experiment. The red part is the experiment that has been conducted on the battery, and this part is the simulation. The green part is our simulation, and this one is the simulation of the MIT. In the next stage, we want to work on the optimization problem. We divide the shell thickness into 17 sections, and we want to obtain the optimal result for the shell thickness. We know that the shell thickness uh, is varied, and we want to obtain the optimal results. But at this case, we do not want to just consider a quasi-static loading. We want to consider the impact loading. If we consider that at this stage, the punch is coming with a constant velocity, and we will see the results. So the first objective function is we want to minimize the maximum displacement of each node. So, and the second objective function is the weight of the whole shell casing. And regarding the lower boundary and the upper boundary, we consider that based on the literature review, the maximum amount of the shell thickness was less than half a millimeter, so we consider the upper boundary as 0.54 and the lower boundary as 0.18 for each section. And we need to, since we want to do or implement impact simulation, we will use LS-DYNA, which will have some better algorithms for simulation of the impact analysis. And for each iteration, we get the results, and we will store the data to MATLAB. And after doing the pattern search optimization technique in MATLAB, we will input the new results to LS-DYNA, and we will get the resultant maximum resultant force. And again, we do it again more than 60 times. We do this, and this will be the results. We have conducted the results around 60 times. It takes around 2 weeks for a simple computer at the university, and you see that the for each section the thickness is varying like this in an oscillation way. The interesting point about the final and optimal result is that you see some kind of oscillation between the thickness here, and you see here it's going up and going down, going up, going down, up, down, up, down, up, down, and this is the optimal results we got from the pattern search methods. And we don't know why we got this result, but when we go through the result by conducting the numerical test in the LS Dyna, we found that we also found that it might also have some positive impact on the crashworthiness test. You see that here the progressive collapse is associated with the peak forces at the resultant force in the figure that we got from the Ellis Steiner results. Actually, I have to tell that this kind of test, this crashworthiness test, which can be conducted by putting a plate on top of the battery, is another standard test for finding the structural integrity of the lithium-ion battery out of those four standard tests. Future work, we want to put those new batteries that we developed inside of the Tesla cars. You see that these two tests has been conducted in Australia, and we are conducting the simulation of the uh, test here using Palestina. We will transfer the velocity that is exerted on the lower part of the battery, and we want to see what would happen if we use these kind of new batteries. We have more than 200 batteries at this case, and these are the x velocity of the nodes at the bottom, some nodes at the bottom parts of the battery. Actually, you can see the simulation that we have done until now. Okay, the conclusion: force displacement prediction is a critical evaluation criterion for assessing the accuracy of the battery simulation, and the comparison in our case focuses on how well the proposed simulation in our work aligns with the experimental force displacement data in comparison to the existing method. uh, in this case, I am referring to the MIT simulation, and we use the multi-objective optimization analysis, and feel indicated that oscillation in the thickness design leads to an optimal result. We have done also uh, the GA, and we got similar result. We will get similar result if you do that. Hope so. Thank you all for your attention, and I am now open to any questions you may have.